In part 2 of this 3-part video series on simple linear regression, we'll turn our attention to numerical summaries, correlation in particular. From a scatter plot in part 1, we observed a strong positive linear relationship between penguin body mass and flipper length. But the term strong is both vague and somewhat subjective. Thus, we want to measure more precisely just how strong the relationship is. To this end, correlation provides a numerical measure of the strength and direction of the linear relationship between two quantitative variables, y and x. To understand this metric, consider scatter plots for 4 different example relationships. The first pair of xy variables at the left has a correlation of negative 0.6, represented by lowercase r. At the other end, the last pair of variables has a correlation of positive 0.95. In between, the third pair has a correlation of 0.2, and the second pair has a correlation of 0.05. Based on these 4 examples and your intuition alone, I want you to pause your video and try to answer the following questions. What values do you think that a correlation can take? What's the biggest it can be? The smallest? What do you think the positive-negative sign of a correlation indicates? What's the difference between negative and positive correlation? And what do you think the magnitude of the correlation, or its distance from zero, indicates? Let's check your intuition. First, correlation ranges from -1 to 1. The sign of the correlation indicates the direction of a linear relationship. For example, a correlation below 0 indicates a negative relationship, and a correlation above 0 indicates a positive relationship. Further, the magnitude of the correlation, or its distance from 0, indicates the strength of a linear relationship. At the far right end of the spectrum, a correlation of exactly 1 indicates that there's a perfect positive linear relationship between y and x. All data points fall exactly on the trend line. At the other end, a correlation of -1 indicates a perfect negative linear relationship. Mainly in these cases, x is a perfect predictor of y. And in the middle, a correlation of 0 indicates that there's no linear relationship. A linear representation of the relationship would have a slope of 0. But in practice, we tend to observe relationships between these extremes. In general, correlations close to 0 indicate a weak relationship between y and x. Correlations close to -1 or 1 indicate strong relationships, and correlations in between indicate more moderate relationships. Let's apply these ideas to our penguin data. Pause your video and take a guess at the correlation between body mass and flipper length. Do you think it's positive or negative? Do you think it's strong, moderate, or weak? And precisely what value do you think it has? Calculations show a correlation in this example of 0.873. That is a strong, positive, linear relationship between body mass and flipper length. In closing, I want to emphasize some limitations of correlation. First, correlation does not imply causation. That is, observing a strong correlation of response variable y with predictor x does not imply that x causes y. Second, correlation can only be used to measure the strength of a linear relationship between a quantitative y and one quantitative predictor x. It cannot, for example, be used to quantify the strength of a nonlinear relationship. For example, recall the pair of variables here. They had a very strong quadratic relationship, but since that relationship is not linear, it had a very weak correlation of only 0.05. Similarly, correlation cannot be used to quantify the strength of a relationship of y with a categorical predictor x, for example, between penguin body mass and species. Nor can it quantify the strength and direction of relationships of y with multiple predictors. Finally, correlation calculations are sensitive to outliers. One or more unusual data point can skew the calculation, resulting in a misleading correlation. I'm going to conclude this video with a formula for calculating correlation. For the purpose of Introstat, this formula is optional. However, if you're interested in mathematical details behind our work, or you may go on to study more statistics or other quantitative topics, I encourage you to stay on the video. Otherwise, feel free to stop at this point. To begin, suppose we have a pair of n data points on variables y and x, denoted y1, y2 up to yn, and x1, x2 up to xn. Focusing on each variable alone, we can calculate the sample means and standard deviations. We denote the sample mean and standard deviation of the y values as y bar and s sub y. Similarly, these quantities for the x values are denoted by x bar and s sub x. Next, within each variable, we can calculate the z-scores of the individual observations. Let's focus on the z-scores for our y values. To calculate the z-score of y1, we subtract the mean of the y values, y bar, and divide that difference by the standard deviation of the y values, s sub y. In words, then, this z-score calculates the number of standard deviations that observation y1 falls from the average y value. Generally speaking, then, the further a sample y value falls from the average, that is, the more extreme it is, the further its z-score will fall from 0. Finally, we can use this information to calculate correlation. In words, the correlation is essentially, but not quite, the average of products of the y and x z-scores. For example, the first term in the numerator here multiplies the z-scores of the y and x values for the first data point. We add that to the product of the z-scores of the y and x values for the second data point, and keep adding up the z-score products from the first to the final nth data point. We then divide the sum of z-score products by sample size n minus 1. That is, again, correlation is almost, but not quite, the average z-score product. Dividing by n, not n minus 1, would make it an actual average. Finally, the final piece of the equation expresses this calculation in shorthand notation. The correlation R is obtained by summing up the product of z-scores for the y and x variables, then dividing by sample size n minus 1. And that's how it's done.